Now let's look at a system with complex eigenvalues. Let's look for the solution of dx dt equals negative 1/2 x plus y, and then dy dt equals negative x minus 1/2 y. So if we write this as a system, we end up with dx dt equals, let's see, this would be negative 1/2, and then 1, and then negative 1, negative 1/2, and we have x and y. So I'm not going to spend too much time on finding the eigenvalues and eigenvectors. We've done that a lot. So the eigenvalues, you can check it yourself. The eigenvalues are lambda equals negative 1/2 plus I, and lambda equals negative 1/2 minus I. Okay, so the eigenvectors just like the eigenvalues are complex conjugates of each other, the eigenvectors behave the same way. It's going to be v1, let's call it v1 equals I, no, 1 and I, and v2 for the second eigenvalue, v2 is 1 and negative I. Okay. Now, one way of writing this is we're going to write it as 1, 0 plus I times 0, 1. All right, that's 1I. We're going to write it as 1, 0 plus I times 0, 1. And 1 negative I, we're going to write it as 1, 0 minus I times 0, 1. Okay, so again, they look like complex conjugates of each other, the two eigenvectors. Okay, we're going to call these, we're going to give names to this. We're going to call this vector A, call this vector B. So this is A over here and B. So this is like A plus IB plus I times B, and this is A minus I times B. Okay, vector A, vector B. Remember that. Now, we're going to define two vectors now. The two vectors we're going to define are P of t. P of t is A, vector A, times cosine of beta t minus vector B, sine of beta t. And we're going to define Q of t as A times sine of beta t plus B plus cosine of beta t. All right. Why am I saying all this? I'm going to assume that if we assume that our eigenvalues are alpha plus beta I and alpha minus beta I, then define these two quantities. All right, define these two quantities. So in our case here, our alpha is going to be, alpha will be 1/2, and our beta here is going to be 1, right? So we define two vectors, P of t and Q of t, all right? Then, if we define that, our general solution is going to be C1 e to the alpha t P of t plus C2 e to the alpha t Q of t. That's it, right? You have your eigenvalues, get your eigenvalues, get your eigenvectors, name them, name the parts of the eigenvectors, the real part, which is A, the real part is A, the imaginary part is B, and then name your eigenvector, the real part of your, get your eigenvectors, the real part is A and the imaginary part is B. Your eigenvalues, name the real part alpha, the imaginary part beta. Then define P and Q as follows. Then your solution, your general solution is this. This is equal to your x of t. Your x of t is this. Okay? So, for our problem, we now have a way of writing on the solution. Let's go back to our problem. For our problem now, P of t is A cosine of beta t. So it's going to be 1, 0 cosine of t minus B sine of beta t minus 0, 1 sine of t. And then our Q of t is going to be 1, 0 sine of t plus 0, 1 cosine of t. Okay. Now our solution, we know that our alpha is 1/2 and our beta, our alpha is actually negative 1/2. Alpha is negative 1/2. And our beta is 1, okay? So our x of t now, x of t, which is C1 e to the alpha t, which is negative 1/2 t, times P of t. P of t, let's combine the two vectors to get, this is just going to be cosine t minus sine t, okay? And this is just going to be sine t and then cosine t, okay? So we just get cosine t here minus sine t, right? Plus C2 e to the negative 1/2 t. Then we have sine t and then cosine t. So that's it, right? So if you want to split it up, your answer is this. This is the vector form, Your answer is x of t is equal to C1 e to the negative 1/2 t cosine t plus C2 e to the negative 1/2 t sine t, right? And then your y of t is equal to C1 e to the, negative C1 e to the negative 1/2 t sine t plus C2 e to the negative 1/2 t cosine t, okay? All right, so you can put it either scalar form or vector form. Now, let's try to sketch the face portrait. So what's the face portrait gonna look like? our eigenvalues have negative real part. Remember that. Okay. Negative 1/2. First of all, let's start with the axis, x-axis, y-axis, x-axis. I tend to want to make the x-axis longer. I don't know why. So we're going to have a spiral. I'll explain that. But first of all, let's pick a point. Let's pick 1, 1. Let's pick the point 1, 1. Go to our equation. At 1, 1, what is going on at 1, 1? You can pick any point, but I just want to pick something that's easy for me. At 1, 1, dx dt, if I plug 1 in there, I get 1/2, positive, greater than 0, right? dy dt, is it positive? 1, 1, yes. dy dt, dy dt dy dt is negative 3/2, which is negative. So we know that at 1, 1, we have something. If this is 1 and this is 1, we have a direction going like this, or going like x is increasing and y is decreasing. So we have something going like that. Y is decreasing. So x is increasing and y is increasing. So our arrow is going to be pointing this way. The direction is just going to be pointing this way. Okay. And generally, this is how the whole thing is going to behave. The whole every trajectory is going to behave. What do I mean by that? I mean that the trajectories are going to be all spirals, and they're going to be spiraling in that direction. I mentioned before that they are spirals. So it's going to come like this, maybe go like that, right? You get another one, another spiral, maybe like this, like that, okay, and so forth. So trajectories are going to be spiraling inwards. This is your x-axis and this is your y-axis, okay? All right. And they're spiraling inwards like that because the eigenvalue is negative. The real part of the eigenvalue is negative. Real part of the eigenvalue is negative. So let's write that down. So eigenvalues are negative 1/2 plus or minus 1i, okay? So real part, the real part is negative 1/2. Right? And this is the reason why everything is going inwards, because the fixed point, equilibrium point, is 0, 0. Everything is spiraling into the equilibrium point. Right? And this is called, this fixed point, 0, 0 over here, is called a spiral sink, right? And it's stable. Stable. Now, let's look at other cases. Let me now copy this, put it right here. So, if we assume that lambda, for instance, is 1/2 plus I, right? In this case, real part, or plus or minus I, real part is positive. Right? Instead of spiraling inwards, everything is going to be spiraling outwards like this. These arrows will become outwards. Okay? Now, let's look at another case. I'm going to copy again. Copy, paste. Okay, I'm going to delete this. Okay. So if we assume let's assume lambda is equal to just I. It's just I. It's plus or minus I. Pure imaginary. Right? In this case, you get like full-on cycles like this. Full cycles. And you can just pick a point to figure out the direction. So it might be like this. See. Okay. So these are the trajectories. Okay. In this case, this is called a center. The point 0, 0, 0, 0 is now called a center. And we say it's neutrally stable. Okay. And here I didn't give a name to this. 0, 0, the fixed point 0, 0 is called a spiral source. Spiral source. And it's unstable. Okay. All right, so that's the phase portrait, the different kind of phase portraits we see for complex eigenvalues. All right, I'm going to stop here. I will see you in the next video.